All right, so let me start my timer. Well, thank you everyone for joining us all today. It's great to be here at like the first Go Remote Fest. I'm thrilled to be able to present to you today. I'm going to crack on because I have quite a bit of material to go through. As Natalie said, today's talk is about maps. A couple of years ago, I talked about one of my favorite language features, that is a kind of a user-facing feature, which is constant. Today, I'm going to talk to you about my favorite implementation detail of Go. Specifically, this is maps. Now, I'm going to be talking about what we call the reference compiler, GC, which is the one that you get on golang.org. If you're GCC Go or maybe TinyGo, things might be a little bit different under the hood, but it would be too distracting to try and cover all the bases. So we're just going to stick with golang.org. So when I was first working on this talk a little while ago, I like to make a teaser, and I said, here's a sneak peek. Here's a sneak peek of it. To which Brad tweeted back, "There's going to be a lot of unsafe." And I mean, to an extent, he is right. There is some unsafe involved, but not as much as you might think, and not in the parts that matter. So let's get into this. To understand what a map type does, the regular map that we use in Go all the time, we need to step back a little bit and talk about the idea of a map function. A map function, the answer is right there in its name. It says it's going to map one value to another. And we do this a lot. We think about this a lot. Like if you use Redis or Memcache or any key value store, you give them the key and they give you back the value. So they are mapping from the key to the value. Now, the implementation I'm going to talk about today, because it's the one that Go's map is based on, is called a Hashmap. Hashmaps has some useful performance properties. They offer, hopefully, order one lookup on average. And the worst case lookup is order one lookup and order n in the worst case. That is, when things are working really well, to execute a map function to go from the key to the value is usually a small constant. And the size of that constant, like how big that order one is kind of part and parcel of the Hashmap design. And the point at which you move from order one to order n is really determined by the quality of the hash function. Which brings us to the hash function. What is the hash function? A hash function takes a key of an unknown length and returns a value based on that key of a fixed length. And we'll see why the fixed length is important in a bit. But now we have two ideas. We have the map function, which maps from the key to the value. And we have a hash function, which when you give it the key, it returns some fixed length value. Now, this value is almost always an integer. We'll see why in a second. And intuitively, like we know what this hashing function looks like. Like we use it all day, every day in tools like Git. We know that every piece of information you put into a commit in Git is given a unique SHA value, and that value is derived from the contents of the hash. So here, when we use Git hash object, the key is the contents of Moby Dick, and the value is the hash of that. So this is an example of a hash function. Now, I mentioned that the property of the hash function is important because it determines how efficient the hash map is. And so hash functions can't just be anything. They rely on two very important properties. The first property is stability. Given the same key, we must always return the same answer. So if we go back to this, like if we hash Moby Dick over and over again and we've got different SHA-1s, that would be bad because we would no longer have a working hash function. So with the same input, the hash function has to return the same output. And this is, as an aside, this is why most map implementations don't let you change the key that you stored in the map. They don't let you have a reference to the key. and they discourage you, like for example in Go, you can't store a slice of bytes and use that as the key, because potentially you could change that. And that would mean that you would change the input to the hash function, you couldn't find the things you'd stored in the map. The second property of the hash function, this is a much more subtler property, is collision resistant. Given two similar inputs, the hash function should return very different outputs. So for example, the result of hashing the number 1 and the result of hashing the number 2 should be wildly different. This is important for two reasons. We'll see in the next slide that the output of the hash function affects the distribution of the how the data is distributed in the map, which gives it its order 1 behavior. And the second one is that in recent years, so-called kind of hash probing or hash spoofing, if the attacker knows your hash function, they could potentially craft input, which will cause all of the results of that hash function to be very similar. This causes poor distribution in your map, and it means that your map functions, instead of being effective lookups, become long kind of linear lookups. And this is a vector for DDoS. Okay, so now we have the hash function. Let's look at the second part of the solution, which is the actual Hashmap data structure. This is the classical way you'll see them described in books. You have an array of buckets, which are basically just pointers to actual buckets. And so in each bucket, we store keys and values. So for example, if we wanted to insert something into this, so we have just a map that's recording stars on GitHub for projects. We have the key. We feed the key to the hash function. We get back some value. It doesn't really matter what it is. And usually that value is either modulo or mask or some property that's used it as an index into the array. So we go to index number 3. We look at the bucket in here, and now it's simply a case of walking down the list of entries in that bucket and putting golang/go and the value into the map. The lookup process is very similar. We have a key, we hash it, we get some value from that hashing. We use that as a mask, and this says that for this key, if this value exists in the map, it will only exist in entry 5. So we've already, this is part of the magic of the hash function, that it eliminates 7/8 of the search space, simply because the value cannot exist in those other buckets. And then it's a case of walking down the entries to find the one that you want. So that's the kind of quick version of a hash map. So they have 4 distinct properties. You need a hash function to hash the key. You need some kind of equality function to compare the keys as you're looking through the bucket to, is this the one that I started with? You need to know the size of the key, and you need to know the size of the value. And this is because, as we saw in the previous slide, if these things are stored in an array, you need to know how far to jump in memory every time. Now, before we talk about the way that Go implements a hash map, I want to give a brief overview of 2 popular languages, which I consider not direct competitors, but they're certainly contemporaries. They're compiled, they're targeted at the same space. If you look into Go's history, they were in use in Google at the same time that Go was invented. So they're probably fairly representative contemporaries. Now, the other thing is that both of these languages use a single map implementation that works across a variety of keys and values. This is because Go's implementation is a single implementation that works for almost all keys and values. So to keep it fair, this is what we're going to do. The first language we'll talk about is C++. Now, not a C++ talk. I'm sure I'll get some of the details wrong. Specifically, C++ doesn't just have one map. Like, why would you? There are many, many to choose from. So the one that I've chosen, which seems to be the closest to Go's implementation, based on a hash map is called standard unordered map. Because this is the declaration for standard unordered map, and because C++ has templates, this is a templated type. And so we can see things like the actual type for the key is part of the declaration. The type of the value is part of the declaration. The hash function, you can provide the specific hash function you want to use when using this map. Otherwise, you get this default standard hash. And similarly, the equality function that you're going to use to compare the key you're looking for to the key stored in the map is also provided. So you spell out all these things to C++ when you're constructing an unordered map. Now, let's just quickly look at how it works. So this is the lookup for the same key. Pass it to the hash function that was provided from the map. So the user can provide whatever hash function they want. Get some hash value. Use that to mask into the array of buckets. And this is where things get interesting. C++ isn't using an array like we saw in the previous example. It's actually using a linked list. And so we use the equality function to compare the key with the key that we're looking for. If not, we follow, this is a linked list, so we follow the chain of pointers and we keep looking until we either find an entry in this link of buffers, or we fall off the end. Now, some of the other parts of this is because this is a templated type, it's constructed when it's declared. All of these things like the hash function, the key, they're all specialized for exactly that map. So if you have a map of, we have strings to integers here, you'll get exactly the code for strings to integers. That's one of the nice things, means that the compiler can leverage a whole bunch of optimizations. The second language I want to discuss is Java. And Java's hash map type is called Java util hashmap. So that's simple. One of the interesting things about hashmap in Java is that it can only store objects, which is kind of fine in Java because almost everything is a subclass of Java lang object. And because every object in Java descends from Java lang object, they inherit hash codes and equal methods. So each object, rather than having to construct the map with a specific hash function and equality, every object knows how to get its hash code and it knows how to compare itself to any other object. So they kind of come built in. That's pretty nifty. However, I said that almost everything in Java is an object. And in fact, there are 7 types which are not. Booleans, integers, shorts, longs, bytes, floats, and doubles are not subclasses of object. They're so-called primitives. And that means you can't use them as a key because they're not objects, and you can't store them as values. And so as part of the kind of boilerplate removal, the magic behind the scenes, when you use one of those types, like you want to go from string to integer, the compiler takes your primitive integer and so-called boxes it, puts it inside a box of a thing, which is an object which represents that integer. Now, all this magic is great, makes it really easy to use, but does generate a bunch of little tiny objects that are kind of created and destroyed along the way. So, you know, that's not great for performance. But let's put that to the side. So a quick look at how Java's hashmap works. Take the key. We ask the key for its hash code. It's great. I mean, keys are strings. Strings know how to hash themselves. We get some value. We, again, take that value, modulo it, get an entry into the list of buckets. And again, Java's hashmap uses a linked list. But you see there, the second entry is it's not the integer 897, it's an object that was constructed from 897. So this is an example of the entries in the map can only be objects, not primitive values, which is kind of a bummer. But apart from that, it pretty much works the same. So we've seen how C++ and Java implement a hash map. Let's take a quick look at the advantages and the disadvantages. C++, the size of the key and the value types and all of those things are known up front. That means your data structures are always exactly the right size. No need for boxing, no need for indirection. And because the code is specialized for exactly one kind of type, the compiler can probably optimize a bunch of logic which would be for more generic, like work with any type. So those are all good things. The disadvantages, because each map is specialized for the key and the value type, if you have a map of strings to int and a map of strings to unsigned int, those are two separate map implementations, completely separate. So if you have n map types, like if your application deals with different kinds of maps, you're going to have n copies of the map code in your binary. That leads to extended compile times. Due to the way that kind of header files and template inclusion works in C++, every time you talk about a map, the code in the header for the map has to be brought in, compiled, and then at the end, the linker has to find all those identical map types and collapse them down onto one. So you do a lot of work up front, and then you do some more work on the back end to reduce that down to one. And probably the most bizarre one as I was revisiting this talk is that standard on map uses a linked list. And linked lists are terrible on modern processors. They cause poor cache locality because a pointer can point to anywhere in memory. And pointer tracing generates a lot of indirect loads. Like you need to know the address of the thing you're loading so you can load the address of the next thing you're loading. That's very hard for processors to do speculatively. So it tends to, a lot of random memory references tend to performance. And here's a sidebar and something that won't work too well here in Radio Land, but as a question to the audience, why has the C++ map used linked list? Like, isn't this a language which is all about performance? Like, why would they use such an inefficient data structure? And the answer, at least it seems to me, is because C++ allows you to take the address of a value stored in the map. So if you look up a value in a map, you can get its address. Seems reasonable. This is actually something that Go programmers want to do all the time. They're kind of a little bit annoyed that if you want to, that you can't take the address of the thing that you stored in the map. And there's a very good reason for that. Because if in C++ or in Go, we let you take the address of a value in map, that means we could never move that value. If they were stored in an array, which is we're going to see in a little bit, then that array could never be reordered because all of a sudden that address would point to a different value. So the reason that C++, I think is for certainly in this implementation that allows you to take the address, to use this inefficient linked list data structure is because it also lets you take the address. And this is one of the reasons why, if you go and read the effective Go FAQ, Go does not let you take the address of map entries, specifically so that we don't suffer this misoptimization. Let's quickly look at Java. Good advantages. One, implementation of a map that works for any subclass. So under the hood, Java's map type only cares about objects. Everything is a subtype of an object. So one copy of Java util Hashmap is compiled and used for every single map in the program. That's good. Less code, better locality. The disadvantage is, of course, that everything has to be an object. So if you want to have, like, even the simple example where I'm just counting up stars, I can't directly store the count of stars. I have to put it inside, I have to box it inside an object. Also uses linked lists. This is probably not a deliberate decision either way. It is probably more that when Java was designed, memory locality wasn't such a problem, and Java being an interpreted language is back when it was designed, that probably wasn't a cost that they could see. But it certainly is not the best for modern processors. But the key one is that because each object that you put inside the map implements its own hash inequality function, those have to be supplied by the author of the class. If you get them wrong, bad things happen. if you have a hash function which is not stable, or you have a hash function that has poor locality so that values are not distributed amongst the map, they all just kind of hash to the same thing, then you're going to get really, really poor map performance. Okay, so let's move to the meat of the matter. Talk about Go's Hashmap. How do we do this in Go? Like, how do we have one type that works for almost all types that you can write about in the Go program? Does it use interface? Like, is map lookup actually just using boxing things to the empty interface? No, the Go runtime does not use empty interface to implement Hashmap. So if you look at container set and container heap, those are terrible. They should never have been in the standard library. That was a mistake. And don't look at them and say, oh, well, that's the, I will follow that idea and extend it into container Hashmap. That is not how maps are implemented inside Go. Does the compiler use code generation? We saw that in the C++ example, every time you have a new map of key and value types, it makes the compiler produces a new map implementation. Does maybe like is map special or something in the Go compiler? Does it generate different maps every time? You know, map of string, map of string to int, map of string to bool. Does it generate them under the hood for you? No, there is only one copy of the map implementation. It's in the runtime package. It doesn't use empty interface boxing. So how does it work? Well, there are two parts to the answer, and this involves cooperation between the compiler and the runtime. The first one is to understand that the code we write on the left, which is our normal Go code, is rewritten by the compiler to these runtime functions. Now, you notice that they're lowercase, and that's because they are just normal Go functions. You can go and read them in the source code, but they're not exported, obviously. So there is a little bit of magic in the compiler that turns the syntax on the left into the syntax on the right. As I said, there's the code for Hashmap. This is all you need. So if the runtime doesn't change depending, you notice that we didn't change. There isn't like it's called map access one. It's not called map access string to int or map access something like that. This rewriting happens for every key to value. So how does that work? The first bit is that we know that v equals m of key compiles to runtime map access key and the address of v. So how does this work? Let's look at the source. This is the signature for map access one. We have a pointer to the key. We have a pointer to the value. So we pass in the key, we get back a pointer to the value. We have a pointer to the map structure, which makes sense, like look in the Hmap for this key and return the value. We also have this thing here called a map type. And map type is the special source that makes this all work together. The map type makes a single runtime Hmap type, the generic type for that map access uses, and it helps it specialize it for any key and value. So instead of there being in your Go program one map implementation per key and value, there is one map type value, and it's effectively a configuration struct. Let's have a quick look in here. As I said, it's a struct. It's just metadata about this particular map. So we have the type of the key, type of the value. And these are so pointers to underscore type. So this is another type declared in the runtime. So therefore, for each type, like every type that you create, there is one of these structures. It tells you things like how big it is in terms of bytes, it has links to the hash and equality functions. And if we go follow this chain a little bit further, we see we have this thing called a type alg. So the type algorithm is just a little structure which knows how to hash. It's a function for hashing the particular type it references and doing the equality for the particular type it references. So there's going to be one of these for each type used in all the different maps in your Go program. And so now we can see how this is all going to work. We have map access. We get the algorithm for the key. We use the algorithm's hash function to hash the key. We mask off the bottom bits and look in the particular bucket to find the correct bucket. And the last bit I want to talk about is there's this kind of extra bit of source mixed into the hash function. We call algorithm.hash. We pass in the key. We also pass this thing called hash0. And hash0 we see comes from the Hashmap. So this is a per map seed that salts. We call it salting when we want to take the same hash and slightly shift its results. And this acts to protect. It adds an extra degree of randomness that the attacker can't predict. I mean, they can go and look in the source of Go and find out and read the hash algorithm, and they could potentially produce a bunch of inputs which could hash together to very close values, but they do not know the value of h.hash0, which is a unique random seed for each different map declared in your Go program, and this acts to counteract that force. So all the bits, pulling it all together, we start by key. We call map type.key, so that's get the algorithm, so that's the algorithm for hashing a string. We get some value, mask it off, look in the bucket. We get to an array now. This is no longer a linked list like we saw in Java and C++, but a good old array that is sized appropriate to the key and the element types. And then we use the equality algorithm for the key to compare against each of the keys, walking our way down the bucket. So that's it. That's the magic. That's how maps work in Go. And so just things to touch on, because this is a talk about the implementation and why I thought that this implementation was worthy of note. Unlike Java, you can use scalar values and characters and integers and unsigns without the overhead of boxing. So you pay a lot in Java for dealing with primitive data types, and in fact encourages you to use more complicated data types, and that just pushes more pushes more onto the garbage collector to clean up those things after the fact. And unlike C++, rather than one copy of the map per data type that you use in the program, in Go we have one copy of this map type value. So instead of one independent compiled maps for all the different types of maps you use in your program, we have just these small map type configuration values which are used in map accessing to get the information that that C++ has to provide at declaration time. Now, that means that there's only one copy of the map code in the runtime. We saw it. And while it can't be optimized to the degree that potentially a C++ implementation could, Go maps are not slow. And they're probably not slow because just for generalized reasons, but they're probably not slow because they can use a much more efficient data structure to actually store the data. There's no pointer chasing and linked list chasing. This is on a 5-year-old MacBook, and these are down in the nanoseconds. It's not those are not terrible results. And just in closing, very, very quickly, please don't interpret this talk that I'm trying to argue that Go shouldn't add generics. I'm just talking about the situations that we have in Go today. But it is important to note that without without having to add generics. Go has avoided many of the pitfalls of other implementations that use generic or templated methods. I showed you the disadvantages of maps in C++. I showed you the disadvantages of maps in Java, and we've managed to avoid many of those without even having to have the discussion about having to write a generic type for a map in Go. And so the thing I want to close on is that I think Go's hash maps are a lesson in good design and just designing within constraints without saying this is impossible. I have to use interface, I have to use empty interface, or this is impossible. I can't possibly even start to write a map in this language because I don't have templated types. Go showed that we could do all these things. There is a little bit of special sauce that linkage between the language and the compiler, but on balance, this leads to a very efficient design, without the memory bloat of Java, or without the compile time overhead of C++. And I think that is definitely something that probably deserves recognition. It's one of, as I opened with, it's one of my favorite implementation features of the language. So thank you very much. I am absolutely at time. I don't think I have any time for questions interactively, but I can probably answer them offline. So I'm going to stop sharing and hand it back to Natalie.
Thank you very much, Dave. And as you said, questions are probably Twitter is the best way to reach you. So if anybody wants to reach you, it's at Dave Cheney. And also if you tag the conference, this will be retweeted. And just a quick information about why this background is related to you. You're one of the big supporters and creators and organizers behind GopherCon Australia and New Zealand. So thank you for all the community work and for that. And to everyone, please.
Let's make sure credit where credit is due. That's all the work of Chewy and Katie, the organizers of the Go user group here in Sydney. So big props.
Absolutely.
Virtual golf clap.